Hello, everyone. My name is Elisa Baum, and I'm GridGain's Director of Product Marketing. We'll begin in just a moment, but first I'd like to conduct a bit of housekeeping. Can you please raise your hand using the hand icon located in the GoToWebinar control panel to let me know if you can hear me? And let me take a look. Okay, great. I see hands. Next, during this webinar, you will be on mute. Should you have any questions during the discussion, please enter them in the questions field within the control panel. At the end of the webinar, we will take time to answer as many questions as possible, and those that aren't addressed will be answered in a follow-up blog entry on GridGain's blog. In addition, a recording of this webinar will be made available to everybody within 48 hours. I would like to thank you for attending today's webinar, The Emergence of Converged Data Platforms and the Role of In-Memory Computing. It's being presented by GridGain CTO Nikita Ivanov and 451 Research Director Matt Aslett. And with that said, I'll turn the floor over to Matt. Go ahead, Matt.
Thanks, Lisa, and thank you everybody for joining us on today's webinar. So as Lisa said, I'm Matt Aslett. I'm Research Director for Data Platforms and Analytics at 451 Research, and I'm going to kick off the webinar with just a kind of an overview of the landscape as we see it in terms of converging data platforms and touch on the role of in-memory in that. Before I get into the presentation itself, just very briefly to introduce you to 451 Research for anybody who has not come across the company before. So we're an IT research and advisory company focused particularly on innovation and emerging technologies. We were founded in 2000. We've got over 250 employees, including over 100 analysts, and over 1,000 clients, including technology and service providers, corporate advisory, finance, professional services, and IT decision makers. The final data point from this slide I'll just point out is the next one, 50,000 plus IT professionals, business users, and consumers in our research community. And so these are not necessarily clients of 451 Research, but they are IT practitioners, people out there using software, hardware, services that we are engaging with in terms of doing surveys and interviews, and they increasingly help shape our view on the market. So a very important part of 451 Research going forward. So on to today's presentation, and what we're talking about today is converged data platforms, and this is something we've been looking at over recent months within 451 Research, particularly looking at the way in which some of the emerging data platforms have the potential, or in some cases already are, converging with some of the existing data platforms, and how organizations are looking at their overall data management, data platform estate, and thinking about that as more of a cohesive whole. As you can see, some of the core technologies we're talking about here: distributed grid cache technologies, NoSQL, relational operational databases, analytic database, Hadoop, stream processing, and then the last one, which is a little bit of a sort of an outsider and more of a long-term perspective, is containerization. We sort of threw that in because we think it will have a significant role to play, and it certainly has some interesting connotations in terms of the convergence of the overall data platforms. If we start to think about how this convergence is evolving, historically, obviously, the data platforms landscape has been dominated by relational operational databases and analytic databases. They make up the bulk of the market, and we expect that to continue. But what we've seen obviously over recent years is some of these technologies have been around for some time, but they're getting more and more important in terms of enterprise deployments and in terms of providing an alternative, particularly for new application development projects. So stream processing, obviously about real time, that obviously a significant driver for distributed grid cache. NoSQL, obviously there's a bunch of drivers around there, and we could do a whole separate presentation on that, as we could on Hadoop and some of the other things here. And obviously, as I mentioned, containers, more of a long-term potential impact. And what we've seen obviously is that there is a great potential being driven by some of these emerging new platforms. So this here represented on this chart is data from our 451 Research Market Monitor, excuse me, through which we provide revenue estimates and growth estimates for all of the products and technologies that we cover within the data platforms and analytics team. And so here we're looking at data related to, so just the core emerging data platforms that I mentioned. So Hadoop, event stream processing, NoSQL, data grid cache, and NewSQL. And as you can see, combined, those represent revenue of about excuse me, $3 billion in 2015, but we could see that growing towards $14 billion in 2020. So there's $11 billion of sort of, as the term we use is value creation, or revenue being generated by these emerging and new data platforms across the next 5 years. Of course, as I said, that the market as a whole will continue to be dominated by some of the incumbent platforms, relational analytic databases, but there is clear value being generated by these new data platforms, particularly for new applications. So here we're looking at the revenue being generated by each of those segments individually. What is more interesting, of course, from our view when we talk about converged data platforms, is the potential that they have in combination. And what we clearly see is that there are integration points between these emerging technologies, and there are various integration points, but that's really only half the story. I mean, running distributed grid cache alongside or on top of the relational database, running Hadoop alongside, it's interesting, and that's what we see a lot of companies, enterprises today. They're looking at all these individual platforms, they're exploring how they can use them for individual applications, and they're looking at how they can integrate them. The more interesting story, perhaps in the long term, is not how they can be integrated. Excuse me. Sorry, frog in my throat. As I say, the more interesting view, perhaps in the long term, is not just how they can be integrated, but how enterprises come to think of them more as a cohesive whole. And that's something we've seen, in conversations we've had with enterprise clients over recent years. The way they're looking at their long-term investments in their data platforms and their data landscape is in terms of some of these technologies coming together to create at least a kind of a logical whole. I'm very sorry about this. I'll do my best to stop coughing. Let me just pause for a second. Okay, so we've been covering this, as I said, for a number of months, and we looked in particular towards the end of last year at this whole convergence issue, and we published a series of reports. You can see three reports we published at the time, looking at how all these technologies have the potential to come together. There's a URL there, bit.ly/451 converged, and if you're a 451 client, you can go there and you can get to part 1 and you can read through, click through to 2 and 3. If you're not a 451 client, if you go to that address, you can still sign up for just to have access and to go on trial. So there's a lot more detail, obviously, than we're covering in this webinar in terms of how we see this evolving. And so if you are interested, do visit that URL and you can find out more. The fundamental issue is perhaps, why do we see all these converging? I mean, there's some technological issues behind that, but actually it's really about business issues, as it so often is. And we see there's 3 core drivers that are pushing this convergence of these data platforms. The need to accommodate different data types, different data formats, and data from different from different applications and workloads. The need to drive operational efficiencies. So clearly there are investments in existing technologies, there are investments being made in emerging technologies, and obviously organizations want to be as operationally efficient as they can, and bringing some of those capabilities and functionality together is one way of doing that. And then lastly, it's about enabling variable workloads. So I think, well, one of the, this is still something that's evolving, but gone are the days where there was a fundamental separation of perhaps transactional and analytic workloads. There's still a time and a place for separation of those workloads for individual applications, but what we see is a lot more organizations want to get faster insight, faster analytics on their operational data, and so that's that business driver is driving the convergence of the technology to deliver both of those capabilities, and add into that the different formats, different data types, and the work operational efficiencies, and that's when you begin to see this sort of larger convergence across the different segments of data platforms that we illustrate here. To go into each of those in turn and sort of talk a little bit more detail about how we see this convergence playing out. So we start with NoSQL, and the reason we start there is because we've seen convergence sort of within the NoSQL space, if you like. We saw that polyglot persistence initially drove the expansion of the database market within NoSQL. So specialist databases and multiple data models, document databases, graph databases, wide column stores, key value stores. And we saw there was a lot of interest, obviously, in using multiple databases to support an individual application in order to take advantage of those multiple data models. What we've seen is that having multiple databases can lead to operational complexity and inflexibility driven by interdependence of those multiple databases. And so we've seen a shift towards multi-model NoSQL databases, multi-model enabling the flexibility of polyglot persistence and being able to support multiple models without the operational complexity that is required by supporting multiple databases. So that's, even within the NoSQL space, we've seen some convergence. Obviously, we think about NoSQL as it relates to relational SQL databases. There's clearly some convergence going on there as well. We've seen relational databases adding characteristics of NoSQL databases, particularly in terms of sort of key value access and also being able to store JSON documents. We've also seen the NoSQL database vendors adding support for SQL, or at the very least SQL-like query languages, in order to take advantage of integrating with existing BI tools and having a supporting languages that people have experience in and that are familiar to them. And we've also seen what we would describe as sort of multi-model, multi-mode databases emerge that support not just a combination of NoSQL and SQL, as I said, especially JSON and key value, but also other specialist workloads. So things like time series data, things like geospatial analysis and queries. And so, the relational database has evolved over many years to take on support for things like objects and XML, and we see that continuing in terms of support for JSON and time series and other approaches, and we also see the NoSQL databases heading in the same direction. Analytic relational operational database convergence, I've already touched on this a little bit. Obviously, for the history of the database market to date, we've seen this typical separation of operational and analytic database workloads. In some cases, it still makes absolute sense for that to do so, but there are use cases increasingly where organizations want to query their operational data in inverted commas in real time. And what we're seeing is also the emerging database vendors taking advantage of in-memory and advanced processing performance to deliver that combined operational and analytic processing. For historically, it just hasn't been possible to support operational and analytic workloads in the same database by and large because of the performance hit you took when trying to do both at the same time. Distributed grid cache technology has obviously been around for many years. Historically, we've seen them deployed separately, in combination with, but separately to a relational database, specifically to provide non-persistent distributed data grid layer that sits above the underlying database. What we've seen is, some of the in-memory databases have added the ability to act as an in-memory cache, or some of the data grid and cache technology providers have added durable database capabilities, specifically GridGain and Pivotal with Gemfire, for example. And so, there is this, the lines are blurring between what is a database and what is a data grid or a data cache. And another thing we've seen, specifically within financial services as it happens, but I'm sure there are other examples in other industries, is increasingly organizations that have made a significant investment in memory distributed data grid technologies, seeing that as their primary data layer. Even if they're still running that alongside a relational database, disk-based database, that becomes kind of the back-end data store, and the in-memory distributed grid becomes for them the primary data layer, and can provide a layer that crosses multiple data platforms in the background. Hadoop is obviously a key data platform for the future as we see it, and by that I mean Hadoop and Spark and the whole Hadoop ecosystem. And clearly that is a primary area of focus for Convergence, and we laid that out here, starting from the top, in terms of sort of data grids and cache Hadoop convergence. We've seen Apache Geode, Apache Ignite become part of the Apache big data ecosystem, if you like, part of which is driven by the ability to integrate with Hadoop and provide caching and data grid capabilities on top of the Hadoop distributed file system. From an operational database perspective, we see Convergence. Clearly NoSQL databases have had a role to play alongside Hadoop for a long time. Apache HBase, for example, Cassandra, MapRDB, and others, including MongoDB. And we've also seen very much earlier stages, but the emergence of some interesting efforts to combine the benefits of a relational operational database with Hadoop and Hadoop distributed file system. So companies like Splice Machine, projects like Trafodion and LinuxScale, another company there. Obviously, a lot more activity to date has taken place in terms of analytic database and Hadoop convergence. Clearly, well suited for at very least integration, and we see that going forward with increased convergence as well. Started with kind of connectors. Pretty simple. Get your analytic database talking to your Hadoop cluster, be able to move data in and out as required. Moving on from there, we saw a lot of investment in recent years in SQL on Hadoop, more about bringing the skills and the expertise of the people and the tools that surround that analytic database to the Hadoop ecosystem, to the Hadoop environment, enable organizations to actually be querying data in Hadoop using the same skills and the same tools that they have previously used to query their data warehouse. Still initially sort of separately, but with federated query, we say that the taken to its kind of next step, which is about organizations looking to query both the analytic database, data warehouse, and their Hadoop environment, at the same time with the same query. The last point here is about sort of columnar storage within Hadoop itself. Again, this is sort of very early stages, but it's interesting if you look at Apache Kudu, and especially when you think about the potential combination of that with SQL on Hadoop, that what you've got there is basically a SQL query engine and a columnar storage engine. Effectively what we would previously use or think about as being an analytic database, but clearly exists in the Hadoop environment. So that again, this is clearly an area where we're going to see increased convergence over time of some of the core technologies and some of the foundational capabilities. Stream processing, again, obviously event stream processing, complex event processing, been around for many years. Traditionally, we've seen those as kind of niche technologies, again, used primarily in financial services, or where there was a real requirement for low latency data processing, high performance applications. What we're seeing is, in other industries, there's a growing interest and growing understanding of the need for more frequent analysis of real-time data streams, and that's pushed data stream processing into the mainstream. We see, again, a lot of those projects are part of the Apache sort of community, and therefore with tight integration with Hadoop, and a lot of organizations exploring what some refer to as the Lambda architecture, but however you want to describe it, both real-time and batch processing in a single environment. And so clearly, a lot of scope for increased convergence there. And lastly, containerization. As I said, this is more of sort of a longer-term impact, but we do see some potential and some interesting opportunities here. There's emerging projects like Flocker from Cluster HQ, which enable, more persistent data storage within a Dockerized environment or containerized environment. There's Apache Myriad project, which enables Yarn to run elastically in Dockerized containers on shared data infrastructure resources managed by Mesos. So that's more about sort of Hadoop itself running within a containerized environment. We're also seeing, Docker support in Yarn itself. So within Hadoop, enabling some of the workloads to run as containers within Hadoop, managed by Yarn. The advantage there being about isolation of resources and preventing sort of some of the issues that can occur when you've got different processing engines that are competing for resources within Hadoop itself. So these are sort of, as I've outlined there, some of the key areas that we see that are coming together. And as I said, it's really our sort of research and focus on this is driven not just by some of what the vendors are doing, what some of it's happening with the technology convergence in terms of the open source projects, but also with the discussions that we're having with some of our enterprise clients about how they are increasingly viewing their landscape as a kind of a single logical whole, particularly for, as I said, new application deployments. And what we expect to happen over the long term is increased convergence being, driving through with those deployments, and then, obviously in the longer term life cycle, some of the existing data processing infrastructure to be, to be retired as in the natural course of its life cycle, and so that the world will. It is going to take some time, but the world will slowly become increasingly converged. Excuse me again. Finally, I know Nikita's going to talk a lot more obviously about the role of in-memory, but just wanted to just briefly touch on, our perspective on this. What we see is, obviously, I've already mentioned, in-memory several times in my presentation, and we do see that memory and the lower cost of memory and the companies taking advantage of in-memory processing is a key enabler for data platform convergence. As I mentioned, we see a new breed of data platform vendors taking advantage of improved performance in their hardware, memory, and processor performance to the extent that they're able to support transactional and analytic workloads, as well as obviously grid, cache, stream processing, and MapReduce and other batch processors as well at the same time. And importantly, what we see is enterprises not necessarily abandoning investments in disk-based systems, as I said, but if you're talking about new applications, new projects, new data processing platforms, then it makes sense, given the trends that we're seeing, for in-memory data processing and analytics to be a key consideration for application development projects and to be a focal point for architectural rejuvenation. So that very much a lot of organizations thinking about creating an in-memory data processing layer, and then thinking about the use cases that they and the technologies that they want to adopt in order to take advantage of that layer. So that comes to the end of my presentation. So I want to thank you again for your time. Apologies again for the frog in my throat. I'm happy to take questions as we get to the end of the presentation, but for now I'll hand you over to Nikita, who can talk about where GridGain obviously fits within the kind of landscape I just described. So again, thanks for your time.
Thanks, Matt. Good morning or good afternoon, everybody. My name is Nikita Ivanov. I'm a founder and Chief Technology Officer of GridGain Systems. So I'm going to follow up on what Matt excellently described as this concept of a converged data platform. And I'm going to give you basically just an example of a product or a project that in many ways follow in steps with what Matt just described as this emergent idea with convergent data platform. We look at a slightly different angle, predominantly with focus on in-memory and kind of driving from in-memory idea outwards. But nonetheless, as you will see throughout the next 15-20 minutes, most of the components that Matt described are there in our product, and that's why we're pretty much excited that it's not only us driving this idea, there is a bigger analyst community that's actually seeing exactly the same ideas, talking to customers and IT professionals. So very quickly, we'll talk about some of the history of the project. It's pretty interesting, the GridGain project and the product, and it's built on Apache Ignite, has a pretty long history, and we'll talk about some of the key components about what we call in-memory data fabric. And you will notice that we'll have many of the same components that Matt described in our product today, from the compute and data grid to service grid to streaming, complex event processing, Hadoop and Spark acceleration, and things of that nature. So we'll stick on this project for now. I'm on this slide, and I'll start by briefly talking about a history of the GridGain. So GridGain started as an open source project roughly about 10 years ago in 2005. And it's basically has been steadily growing acceptance, and a couple of years ago it joined Apache Software Foundation, the same body that produced the Spark and Hadoop and Cassandra and many other projects. And it was renamed Apache Ignite so that GridGain company can retain its name. So essentially right now, GridGain is based on Apache Ignite. Think about this like Hadoop, Cloudera, and then Apache Ignite and GridGain. That's the same thing. So fundamentally, we're based on Apache Ignite. And what is Apache Ignite? When I say Apache Ignite, it's synonymous with GridGain, so I'm going to use it interchangeably, GridGain and Apache Ignite. So what is Apache Ignite? Apache Ignite essentially what we call is a data platform, in-memory data fabric. We use word fabric. Again, it's just, we can easily replace with the platform here. The idea with memory data fabric is that essentially it's a type of software, it's a distributed Java-based software, JVM-based software, that fundamentally sits in between your variety of data sources and your applications. Data sources on the bottom of this picture, it could be practically anything today. It could be any SQL database, could be a NoSQL database that's a disk-based, could be any kind of Hadoop infrastructure, could be straight file system. And on above the fabric, there are all your applications, and we work with a variety of different applications, whether it's a SaaS and mobile application, or IoT, or just traditional enterprise applications, a variety of different languages that we support to talk to the fabric, from a JVM-based languages, Java and Scala and Clojure, to a .NET and C++ and straight SQL, and so on and so on. So the fabric itself, what does it do? It actually provides you two fundamental things. It provides you speed and scale. It provides you speed by moving data from slow disk or flash-based block-level storage into a byte addressable DRAM across many computers. And as you probably can guess, the speed of DRAM is over 1 million times faster than speed of access to a block-level flash or let alone spinning disk devices. We also provide you this scale to this processing and computation because we're parallelizing this process. We're not only moving data, in one computer. We basically create this fabric out of, dozens and times hundreds in our largest installation with 2,000 physical servers in the cluster. And that gives a tremendous parallelization, tremendous parallelism into the system, and that, as a consequence, gives you great scalability. So when we talk about in-memory systems, probably one of the most important thing to remember is that it brings or gives you two fundamental advantages. It gives you unprecedented speed and gives you an awesome scalability. It's interesting to note that when we talk about speed, almost everybody makes a claim about speed. What's really unique about a memory system is that if you think about it a little bit deeply, in-memory systems is the last frontier in terms of where you can keep your data. Think about this. In the last 50, if not more years, we went through from external tapes, late 50s, early, mid-late 50s. Then the hard disk came around, and IBM 360 really revolutionized that with Winchester disks around late 60s, mid-70s. So we had, hard drives, and then hard drives grew in performance, and then, mid-90s, late 90s, flash came around and became prominent, and we kind of were moving data closer and closer and closer to CPU, and make this medium of storing faster and faster and faster. And so today we arguably in an era of in-memory storage, where we store our data in a physical DRAM of a computer across multiple computers to gain capacity. And the natural question, where else can we go? And if you think about it, it's about the only physical place in the modern computer architecture is the own CPU cache. But it's very small due to physical limitations, only about 2-3 times faster than DRAM. So what's interesting about in-memory processing or in-memory data storage is that this is actually the end of the story. This is the last frontier in terms of the data storage in a computer architecture as we know it today. There is nowhere else to go unless we fundamentally change our computer architecture, which probably would not happen anytime soon. So unlike Flash, which is clearly a transient technology, in-memory storage is here to stay, especially with the new types of RAM that's coming up on the market, with non-volatile RAM, with all the different types of RAM that's coming up rapidly into availability. In-memory computing become a fundamental trend in how do we keep the data, and therefore how do we process the data. Naturally, not only the speed of in-memory processing is important, but it is for the first time a fundamentally different way to process data, and that comes from the fact that RAM is byte addressable. We've spent the last 50 years dealing with the block level devices, which is the tape or a disk or a flash device. Those essentially your file systems, and you deal with those data storage systems as externally. You have to constantly marshal and demarshal your objects from and to those disks, and because naturally the representation of the objects in RAM is completely different from representation objects into the external block level devices, whether the tape, disk, flash. So for the first time, we have a data storage system that is completely compatible. As a matter of fact, it's the same as the one where we used to actually run our code, where the code lives. The code lives and ever lived, since the first days of computers in RAM, into the random access memory of a computer. But now we keep our data there, and that opens up the tremendous possibility to optimize data processing, because no longer we have to read kilobyte of data just to change 1 byte. We can literally use the point arithmetic and change that byte instead of milliseconds, have nanoseconds latencies. So all this kind of introduction why memory computing is important, I think is valid and it is important, because unlike any other previous technology, storing data in the distributed in-memory cluster is a fundamental frontier in terms of how do we store our data for years and years to come. There is literally nothing physically else available to do it, and memory will get faster, capacity will grow. Just one more last example, we recently tested with some of the Fujitsu boxes servers. Imagine this, you can buy today a server from Fujitsu with 64 terabyte of RAM. It's a single server, 64 terabyte of RAM. Runs standard Solaris, runs Java, you can do whatever you like. 64 terabyte of RAM is available today. And that's just the $1. Needless to say that anybody from Azure and Amazon already have a very nicely priced, instances with, 16 and 32 terabyte gigabyte of RAM if you need it as well. So with that having all said, so let's just go ahead and talk about what is the in-memory data fabric from GridGain or Apache Ignite can do. So fundamentally, we call it a fabric, and remember that Matt actually mentioned as in-memory data grids in his presentation. Well, in-memory data grids was basically a piece of technology that sort of started the whole in-memory growth about 10 years ago. But we kind of are thinking about Apache Ignite as a more strategic in-memory play, where in-memory data grids is only one component, because only it solves one particular use case of what you can do with the data in RAM. Well, data grid essentially is a key value storage. May or may not have a SQL, may not have transactions, but essentially it's a NoSQL store in RAM. We also have a compute grid, which we'll talk about it. We also have service grade, which is slightly different use case. We have streaming complex event processing, which is a completely different use case as well. We have Hadoop and Spark acceleration, which yet another different use case of how you can use in-memory storage. We have advanced clustering in RAM as well. We have an entirely file system in RAM. Think about this. You can have a distributed file system fully in RAM and have a tremendous performance characteristic on that. This is yet another interesting use case for RAM, and the list goes on. So as you can see, and as you'll see throughout the presentation throughout the next 10 to 15 minutes, this is what basically makes Fabric a fabric. It's not just the one use case of what you can do in RAM. We looked at every possible imaginable use case of what actually people wanted it to do once they have data in RAM, once they have a system that allows them to do that. And we've built those capabilities into the in-memory fabric for Apache Ignite. And obviously it all comes with very consistent APIs, consistent configuration, consistent programming model, and everything else. So although there's a wide swath of functionality, it looks and feels very consistent, and it's very nice and simple to use. Let's start with the compute grid. As a matter of fact, historically, GridGain, many years ago, started as a compute grid. And a typical application of a compute grid is traditional high-performance computing, and it solves a very simple problem. If I have a problem, if I have a task I want to compute on a cluster of computers, let's say on a computer, and it takes a long time, I can split this task into multiple subtasks, execute those subtasks in parallel, get results back, and aggregate into one final result. In ideal, normalized use case, if I have n computers in front of me, I can execute that task n times faster. That's all. That's the entire idea of high-performance parallel computing. This is the entire idea behind a compute grid. The rest of it is obviously a bunch of details. How do we configure, and what do we do? So we have one of the best, if not the best, compute grid in the market. We're the oldest Java-based project that deals with the compute grid capabilities. We have very rich and fat, I would say, APIs for it. We have direct APIs for multiple versions or variants of the MapReduce. Not only we have the MapReduce that's compatible with Hadoop, we also have much more simplified, more optimized MapReduce version as well. We have technology like zero deployment that really eliminates any needs for any cluster-based deployments and whatnot. Obviously, you can do cron-like task scheduling. We have a state checkpoints for long-running tasks. Anybody from biotech and pharmaceuticals, this is the excellent feature for you, because everything in those scenarios takes sometimes hours to process. We have the basic load balancing and automatic failover. This goes without saying, and full cluster management and pluggable SPI design. So we have very rich functional side when it comes to compute grade. You can literally run complex high-performance computations and high-performance compute loads like you would do in those, for example, financial services industries. And you can do that right on a memory data fabric. In-memory data grid, very similar concept to in-memory compute grids, but solves slightly different. Remember that in-memory compute grids solve essentially a problem of a parallelization of computations, right? How do I parallelize my computations? In-memory data grids solve a slightly different problem. It solves the problem of a parallelizing data storage. Imagine again, I have a terabyte of data, and I have 10 computers in front of me, right? So how do I store terabyte across those 10? Well, there's probably multiple ways, but one is the way you can split this terabyte in 10 different parts and store 1/10 of terabyte on each of those computers. And that's exactly what data grid do. But once you do that, it opens the whole can of worms of how do you transact, how do you failover, how do you load balance, how do you query, and there's never-ending list of questions. And this is exactly what in-memory data grids do. It's one of the components in the fabric that deals with the data storage in distributed data storage in RAM across many computers. So in-memory data grid has probably the longest list of features. We can probably talk almost endlessly about. But fundamentally, in Apache Ignite, data grid is the key value store. It's a very important fact because the key value store is the fundamental data structure on which you can layer up different views. You can view in the key value store as a SQL store, for example, where each combination of the key value pairs becomes essentially a table, if you will, in a SQL store. You can also view a key value store as a file system. And so there's a multiple different views that we allow you to have on the same key value store. So you have a key value store, you have a full SQL 99 capability with our system, and also you also have the entire full POSIX file system on it as well, which is, by the way, compatible with HDFS. So in-memory data grid is the transactional key value store. The word transaction is also very important. It's very important to us. We have one of the strongest transaction capabilities in the market today. We have exactly the same transactions that you expect from a database like DB2 Oracle. We have pessimistic and optimistic transactions. We have all isolations level, so read committed, return committed, and serializable. So you have absolutely the same transactional capabilities as you would have in normal databases. So there are two modes in which we work in terms of data grid: partitioned and replicated mode. We have a little bit of time today, so we're going to skip the definitions of that. We work both with on-heap and off-heap storage. It's for anybody who deals with the Java-based applications. You guys know that Java has a limitation of how much on-heap storage it can process. Typically, kind of max out about 10 gigabytes. With our off-heap support, we can use the entire physical RAM on the box. If you have one of those Fujitsu M10 box I mentioned a few minutes ago with 64 terabytes of RAM, you can use all of those 64 terabytes. We're going to use the entire physical RAM on the box, or as much as you configure to us. We definitely have all the kind of low-level plumbing and functionality in data grids with high availability, highly available in-memory replicas for high availability, automatic failover. I already mentioned distributed asset transactions. By the way, we do have, when I say transactions, I want to kind of emphasize here, I'm not talking about eventually consistent transactions, I'm talking about real transactions, something you can move money with. It's traditional transactional behavior that you have. We have SQL queries. We have both JDBC and DBC drivers. So not only we have a SQL capabilities, you can actually connect to our system through a standard protocols like JDBC and ODBC, connect any of your outside external analytical tools to the system and just use this data. So moving on, we also have a service grid, which is yet another, essentially a use case of what you can do on in-memory system. And now you should be getting the idea again about a fabric. That that's why we call it a fabric. It's not a one single use case of what we do. We try to cover many different patterns of what our customers and users typically want to do. And actually, Service Grid is one of the recent additions, and that's exactly what it came out from, from requests from customers. They basically were telling us, guys, we already have GridGain cluster running, and we just need to have some kind of ability to run a service, which is essentially just an objects with some APIs, with certain predefined SLAs. Like, for example, can we run only one instance of that object on each node? Or can we run one instance of that particular object on the entire cluster? And you guys take care of the, maintaining the SLA. If the node crashes, you automatically restart. Or, for example, I want to have only 3 instances of that particular object in the entire cluster. And no matter, what happens to a cluster nodes joining or leaving, you maintain that SLA. So this is exactly what in-memory service grid does. It really gives you a tremendously simple, literally just a configuration, a capability where you can basically deploy any type of services, anything, web service, GNDI service, lookup services, any application services, and just give us, a configuration SLA, and we're going to maintain it. Very simple, very beautiful functionality. Surprisingly for me, it's one of the most frequently used feature. Almost every project where Apache Ignite is used today, service grid finds its use with those projects. Streaming and complex event processing. This is yet another way to process data in RAM. And although there's quite a few different projects for in-memory streaming and the complex event processing, we decided to add basic capabilities, and not so basic as a matter of fact, into the Apache Ignite, because again, it fits the idea of a fabric in a way that basically it's yet another use case of how our customers and users actually use GridGain. They want to basically stream data through the system and have a capabilities for streaming processing. Now, we're not trying to compete with something like Kafka, so we typically use with Kafka, and the Kafka being the buffer in front of us, but we have multiple ingests available built in as well. So the idea of what we do in terms of streaming is 2 things. We have window-based functions window-based streaming. As a matter of fact, you can see this picture on the bottom picture here. And the window actually means like last 100 events, last 5-minute events. You basically define a window on which you want to do the processing. Because the problem with the streaming, or actually characteristic of a streaming processing, is that there is no beginning, there is no end. Unlike traditional databases where you can actually have a table, and you know the size of a table, you can query this table entirely. In streaming, there is no beginning, there is no end. You can never basically have a finite set of data. So what we typically do, what everybody is doing today, is operate on a sliding window. And you define the sliding window, and we actually given you a continuous querying capability. It's a very traditional concept in streaming processing. You define the window, and then you define a query on that window. And the query will call you back with a new results as they appear in that window. So you can say, look, my window is the last 5 minutes of events, and I'm looking for all the events that have the type error. And you define that query, define that window, and off you go. It's a fully distributed, fully parallelized systems, and you get back call when those events popping up. And then you have the entire capability of GridGain with a compute and a data grid and service grid and everything else to do whatever you like with this event. You can dump it on the data grid, you can process later, you can run SQL queries, you can do whatever you like. So streaming is there, predominantly with the sliding window processing and the continuous query capabilities. And it's fully integrated with the rest of the fabric, and that's why it's a component of a fabric. It's a very, very nice addition. We also actually have, and that's probably I think a couple of more slides here. We also have very interesting technology for integrating with Hadoop and Spark, and this again came as a feedback from our customers, and the feedback was pretty obvious that basically when we talk to somebody who's using Spark or Hadoop, we often basically heard that, guys, we love the idea, but we already have Hadoop cluster, and we already have Pig and Hive or hand-rolled MR jobs. We're not going to redesign everything. Can you just split it up? And we thought about it about 3 years ago pretty hard. How can we speed up Hadoop? And if you know anything about Hadoop, in order to do anything with Hadoop in terms of performance, you really have to address problems with first HDFS as a file system and MapReduce as a processing component. So Hadoop consists of 2 major parts, HDFS and MapReduce. And if you were to solve the Hadoop performance problem, you have to solve this too. And that's exactly what we did. We developed a fully HDFS compliant in-memory file system. On some of the operations, we're over 2,000% faster than traditional HDFS. Well, it's not surprising. We work fully in memory, and we can optimize for this type of processing. So we developed a first HDFS compatible in-memory file system, and we also redeveloped entirely a MapReduce subsystem and made it in such a way that it's a completely plug and play. There's nothing to do. There's no code change. There's nothing to do really in a Hadoop cluster. It's a fully compatible, and it gives you a significant performance boost. So again, since we're kind of pressed on time, there's a pretty nice picture on the right on this slide. If you can see this, if you can see those gray lines, this is exactly the execution flow of a traditional Hadoop cluster. You submit the job, it goes to job tracker, it talks endlessly to Hadoop name node, because basically name node manages the metadata for the file system, then goes to task tracker launches the nodes, and it's the entire thing. And if you see the blue line is the only interaction that exists between a GridGain client and a data node. As a matter of fact, unlike many of the modern Hadoop improvements, we actually do in-process execution, so we don't start the nodes every time. So the bottom line, just to give you an example of what we can achieve in Hadoop acceleration, you can download stock Apache Hadoop, run basic example, and also some Pi calculation, then download Apache Ignite, just install alongside the same cluster, change one line in configuration. Very important, there is no code recompilation. You don't even have to have a source code because you don't have to recompile anything. Just change the configuration. Run again about 10 times faster. 10 times faster with absolutely zero effort. Now, your results may vary. Obviously, if your particular Hadoop job spend most of the time in the CPU, we can't change the laws of physics. We cannot make the CPU run faster. But if many of your Hadoop payloads spend a lot of time in I/O ops, basically hitting HDFS and moving data back and forth, those type of jobs can see very nice jump in performance when used with our Apache acceleration. So this is yet another component of Fabric. So by now you should starting to see the whole idea of a convergent data platform, what we call a memory data fabric or platform, is that we are addressing many different types of use cases or patterns, sometimes very unique and strange, right? There's a compute grid and then there's a whole Hadoop acceleration. But nonetheless, those are very much a different takes, different views on the same in-memory acceleration, in-memory processing of data. The last slide I have, as a matter of fact, I think is this one about essentially what we do with the Spark integration. I mentioned to you, Spark is kind of supplementing Hadoop today, especially the MapReduce side of things. And we start talking to a Spark community, Spark users, and one problem came out, very quickly as the top problem. The Spark is no data store. Spark is the processing framework. And as we kind of moving in our Spark usage from kind of, evaluation toy projects to some real projects, people starting to have pipelines of Spark jobs. And what happens in a pipeline when you have more than one job, you have to keep results from one job somewhere until the second job will pick it up. And typically we've been using the Tachyon or HDFS, or we're just dumping it somewhere. And that kills the entire purpose of memory processing, because your job can be pretty fast, but then essentially you have to dump it in some kind of slow system, and then the next job has to read it from the slow system back again. That kills the entire performance. So what we developed a Ignite-based shared Spark RDD, resilient distributed data set. What it allows you to do is to retain results in RAM between two successes and two Spark jobs. And that in return gives you tremendous performance. You can have a pipeline of Spark jobs, and you don't have to lose performance by intermediately storing result sets or somewhere in the slower system. As a side effect, by the way, since we have that shared RDD, you can run SQL on that shared RDD, and our SQL is about between 10 and 100 times faster than Spark SQL. Again, because unlike Spark, we're transactional systems to begin with, and we have a very mature indices implementation in our SQL. Spark doesn't have indices at all. So for Spark, pretty much any single query is a full scan, at least for recently. I know the guys working on it, but at least for now it is this way. And for us, we have very mature indexes implementation in our SQL. So even the SQL on Spark can be dramatically improved by using our integration with Spark. So I believe this is the last slide I have, is just to give you a very quick overview. Again, I don't want to bore you with too much. Where we actually used. And again, this is going to be our GridGain's view, but it should give you kind of a picture of what kind of industry, what kind of customers or applications people use GridGain to solve it. So we used a lot in financial service applications, trading systems, analysis, risk assessment, trading, low latency, high performance transactions, fraud detection, risk analysis, analytics. Basically, any kind of buzzword in the financial service industry you can imagine, we probably use there. We use in one of the probably top 3 banks in the world. We used dramatically in one of the top banks in Europe, in Eastern Europe. So we know this work very, very well. And that's not surprisingly, because for financial service organizations, speed is money, and it has been for decades. So the in-memory computing as the premier technology to gain that speed, to gain that scalability is no-brainer. So it's used a lot in this. I would say probably over half of our customer base, commercial customer base, let alone open source, is from that. We also started to see a lot of uptake in traditional big data analytics. And again, this is a very amorphous theme, but anything from essentially analytics is the big word. Big data or small data, I don't really care. I hate the term. But what the analytics is what's important here. So non-transactional use case, it's anything with machine learning, with a typical analytics, typical large queries, and typical calculations, operational BI, and things of that nature. We're starting to see a lot of traction with IoT, especially in the last, I would say, 12 months. We just recently closed a couple of customers, commercial customers in the space, and I think IoT is really ramping up from kind of a concept to real a segment in the market where we're starting to see a lot of activity. And it's very natural fit for memory computing. IoT is basically dealing with millions, if not sometimes billions, of endpoints and devices. That requires a very sophisticated backend infrastructure. Speed and scale is paramount to be able to process that. Welcome to memory computing. This is the technology for it. Another basically kind of in a subset of customers we've seen in a kind of robust way year-over-year is biotech and pharmaceuticals, kind of bioinformatics overall. This is a traditional, area where there's a lot of data sets to be processed. I always joking to my audience that the pharmaceutical companies today is basically, a predominantly consists of software engineers. It's all software development, and they do process a lot of data sets, and the performance for them is critical. So this is basically a kind of landscape of where we used very quickly. I think it's my last slide. Alyssa, back to you if we have any questions.
Hi there, can you hear me okay?
Yes.
Okay, great. So the first question is there a machine learning library available for GridGain?
Short answer is no. You guys are more than welcome to use a variety of Flink, Spark, Mahout. We don't feel like reinventing the wheel again. I do believe that a ML support in Spark is excellent. So, literally, we don't want to reinvent the wheel. So if you guys need machine learning, Spark, hopefully with our shared IDD support, is an excellent choice.
Okay, and this question I believe is for Matt. What impact will the move to the cloud by many companies have on the development of the Converged data platform?
I think it is a good point. Clearly, along with those core technologies that we talked about, sort of movement to cloud is obviously a driving factor in terms of companies reconsidering their existing data platforms estate. So I think it will definitely have a role to play. I think at this point, there certainly isn't a converged data platform in the cloud that someone could move to. So at the moment, it would still be a matter of, selecting multiple services and multiple service offerings and trying to integrate them, pull them together. Over time, that I suspect that may change as well, and we will see, the emergence of what we might consider a converged data platform in the cloud.
Yeah, I want to add from my side here is that just to give you a kind of flavor of color commentary. 5 years ago, we wouldn't find a single financial service company that would do anything on the cloud for obvious reasons, for data security, regulations, and whatnot. We literally, 5 years ago, our business was bifurcated. Financial service companies would be entirely on-premise, and almost everybody else would be already in Amazon or anything else. In the last 12 months, literally, almost every conversation we have with financial service company, it starts with the number 1 bank, number 2 bank in the world, number 3 bank in the world, number 1 bank in Eastern Europe, and all the way down to smaller companies, all of them moving to the cloud. We just talked to Barclays. The entire Barclays initiative right now globally is to move to the cloud as rapidly as physically possible. And we're talking about Barclays, which is the global behemoth bank. And we've talked to other banks as well, would not name the names, with almost identical corporate mandates. So I believe something has happened, or eventually, pressure has been growing so hard for them that they have to do it. So I think the latest, last holdouts in the whole cloud migration is probably given up, and we're going to see massive adoption of cloud infrastructures in at least from GridGain point of view, our key customers, financial services segment will be moving to the cloud very rapidly.
Okay, and we have time for one more question. So how does the GridGain compare with Hazelcast? What are the pros and cons?
Well, we love Hazelcast. It's one of those, key competitors we have, because additionally to other couple of companies. But again, that's I think where we're different a lot based on essentially our conversation with our customers, because they always look at multiple vendors, including us and some other companies. Hazelcast is predominantly a data grade company, and a good one. We are Fabric. For us, data grade is the component of what we do. And I would say 5-7 years ago, that would be a very fair competition, because back then nobody really needed anything but data grade, and you would be competing in data grade. Today, we hardly find a customer who will be satisfied with just data grade. Almost everybody needs not all of our components, but I would say 2/3 of our components practically used by almost every client we have. It's anywhere from data and compute grid, obviously, service grid. Our Hadoop and Spark integration plays an enormous role in winning customers and winning projects. Often enough, streaming plays an important role, but it's typically a combination of that. And I attribute that to a very simple fact that the seriousness or complexity of use case memory has grown dramatically. It's not caching anymore. Memory computing is not new. If you look 25 years ago, caching is in memory computing, right? And the caching has been in databases for the ages. But the complexity of those use cases grew dramatically. Caching is not even considered to be as even like a use case, because it is so obvious and so ubiquitous. So people are looking for transactions, for SQL, Hadoop and Spark integration. Somebody's asking for machine learning algorithms. Yeah, it's an excellent question. Streaming. Things of that nature. So I think that's a fundamental difference between us and Hazelcast and the companies like Hazelcast. There are single kind of a trick companies that do one particular functions, and we're trying to position GridGain as more strategic play. And we're not only trying to position, we have the technology and software that does that, and that's the biggest difference here.
Okay, well, that brings us to the top of the hour. I want to thank both Matt and Nikita for a great presentation. And audience, thank you for joining us. We hope to see you in a future webinar. And with that said, I will go ahead and close out the webinar. Thank you again, everybody.
Thank you. Have a good day.
Thanks.